Okay, I think we can start. Today we have the pleasure of having Jure Zupan. After doing his education at Ljubljana University, he worked in multiple institutions, including Technion, Carnegie Mellon, and CERN, and received multiple awards, including the NSF Early Career Award. And he's currently a professor at the University of Cincinnati, as well as a convener for CLIC and LHC Yellow Reports, which is, you know.
Yeah, thank you for the introduction. I'm laughing because it's now right now it's a phase transition where these yellow reports are turning into a nightmare. So far it was fun, and now we have to start writing. And also I was very impressed by the pronunciation of my alma mater, Ljubljana. It was perfect. That was really amazing.
My parents went there on vacation, so I remember looking at that word.
Anyway, so what I talk about is, so I have an excuse for talking about this. There's 3 papers, but what I will do is I try to get a bigger picture of like the experimental, where the experimental information is. And also what people are thinking about, what this is new physics, what it could be. So I think my work will be maybe like a 30%. So there will be a phase transition at some point. I'll start talking about details, but mostly it will be a more general review. All right. So the people that did the work is Jerne Kamenik, Yotam Sorek, Admir Greda, which is one of 2 papers, Dean Robinson, and Bibushan Shakya. And so, as I said, a brief introduction, and then I talk about the 2 anomalies. There will be 2 types of transitions. So the quark level, it's B to S plus electronic pair and B to C TAMU. So this is a super general introduction to start with. So all these types of transitions are meant to search for new physics. So the law would be that you search for the stuff that is super suppressed in the standard model, like the flavor changing neutral currents. So in standard model, these are loop suppressed. So this best mixing, you have to do it through a loop. While the 3 levels, so when you have a gluon, photons in the Higgs, they're all flavor diagonal. So the diagrams like this don't exist. So loop suppressed means I gain like an order of magnitude in the sensitivity to the scale plus the secant factors. So you can probe very high scales in principle. And the typical metric element will look like some mixing angles and the new physics scale. Most of these are dimension 6 operators that we talk about. All right, so now if you look at what scales you probe, so I like to show this because it's a logarithmic plot, and what's shown is the so it's this new physics scale where you put the flavor coefficient to be 1. They're dimension 6 operators, but they have different structures. So V minus A, V minus A is this first one, and then there are different chirality structures, let's say left, steps right, and so on. And this is in TeVs. For different systems, so kaon, KK bar, the real part, imaginary part, DD bar mixing, VISA D mixing, VISA S mixing, and you see, first of all, you see that these are high scales, and then the arrows show you the progress in the last decade or so. So it's actually pretty impressive on the logarithmic scale. You see that there was a big progress in some of those. For instance, VISA-based mixing was discovered and then really measured in the last decade. So maybe it is not so surprising that we might start seeing some deviations because progress is being made. So it's really all right. So the present experimental situation is, so many different transitions are measured. You open the PDG. You get dizzy looking at all these decay modes of B mesons. It's pages and pages and pages. But there are 2 transitions, types of quark level transitions, which show 4 sigma-ish deviations from the standard model. the first one is B2C TAMU, so that's a charge current. So in the standard model, you have a W exchange, and then VCB, CKM element, so from B to C, and then just the flavor diagonal coming to tau. So that's the first one. So if you say that the new physics has the same structure as in the standard model, then we'll see that the scale with an order 1 coefficient here would be 3 dB. And then there's the other one, B2S mu plus mu minus, which in the standard model is at 1 loop. There's also CKM suppression, there's the G mechanism. So if you look at the same operator and you say what's the new physics scale in this case, it will be 30 dB. So the difference is, of course, it's a different flavor structure. So this is muons, that's taus, and I have an FCNC, and this is the charge current. All right, so that's what we will focus on. So the two parts of the talk are the two types of anomalies. So we'll talk about B2S mu. So the transition is I take a B quark, goes to an S quark, and a lepton pair. And the upshot is that it's theoretically very clean. So there are very clean observables, and in those observables you see a 4 sigma excess. So this would be, if there's a problem, it's an experimental problem at this point. Or if it's a new physics, you see that you can, since the scales are high, you can have sort of reasonable models for new physics. And then there's an asterisk here, if I put, no? Because there's this same question you can ask that Rabbi asked when the muon was discovered. So who ordered that? It's not really clear that this solves any of the big problems in particle physics. Potentially it could, no? But it's not, with what's being measured right now, there's not a very big connection. All right, so, so I go through the experiments first, but before I do that, we need some terminology. So this, the way this is described in flavor physics is that there's an effective field theory with a common naming conventions. You would integrate out the W and the top and the Higgs, and you would match up onto dimension 6 operators of this type. This would be generated in the standard model. So it's so it's generated at 1 loop. All right, so that's the alpha over 4 pi coefficient there. The GF is roughly 1 over mw squared. So that's the scale. The typical scale is the weak scale. And then we have the CKM elements. You see that there's a VTB, VTS sitting there. Of course, there's also a charm and the up quark. But you can just parameterize everything with the VTB, VTS, and everything else is smaller, actually. All right, and then there are two operators that we generate in these usual naming conventions. They're called, the coefficients would be C9 and C10, so the operators are O9 and O10. Means that there's also O1, 2, 3, 4, 5, 6, 7, 8, no? But the ones that we're interested are only these two. And the difference is I have, on both cases, I have a V minus A quark current. But then there's either a vector or the axial vector current. And in the standard model, this is mostly V minus A. Okay, it's not completely, but it's still mostly V minus A. All right, so the other thing to note is that, and these are all the one numbers. All right, the other thing is that if I couple to the electrons and the muons, as long as you're well above the threshold for muon production, everything should be a universal, right? You couple the same way to electrons as you do for muons. The only thing that breaks it is the mass of the muon. All right, so that would be the Lepton flavor universality is the prediction in the standard model. So if you take the ratios, which are, for instance, now I take a B and I put it in a meson, and an S and I put it in the meson. So for instance, I take a B meson, which is a B quark, and a kaon, which is a pseudoscalar, or a k star, which is a vector meson, and I form ratios of either the muon pair or the electron pair, the ratio, or in the same thing. And this is also, of course, now it's a three-body decay, so I can look at the distribution, for instance, in the Q square of the Lepton pair, so the mass, invariant mass square of the Lepton pair. This was measured in one beam, and this other ratio was measured in two beams. So let's see what the numbers are. So for instance, for RK, so it's one number with one beam that is precisely measured. That's this beam here from 1 to 6 GeV squared. That's the LHCb measurement, and the rest are Babar pairs of previous measurements. So the one that's really relevant is this black thing, and the standard model is at 1 plus percent maybe. Right? And you see that it's more than 2 sigma away. Okay, 2 sigma could be the statistical fluctuation. But then there's a similar thing in RK star. So here, so I've shown a slightly bigger Q squared range here because now you really want to be at the low end where you're below the resonances. The J psi would also give you the same signature. If you decay to B to S CC bar, give you the same signature. Potentially, you could also be this high Q squared. If you integrate over large enough beams, you would also have predictions. But the measurements are here. So these are the theory predictions. So that's the low beam where you see that you start seeing the effect of the muon mass. It's not 1, this ratio. It's different from 1 because the beam goes all the way down to the muon threshold. Okay? And while in the upper beam it's just 1 up to a very good precision. And then the measurements are lower. And the measurements are only coming from LHCb in this case. All right. So that's the experimental situation. All right. So what do we learn? Okay. So you learn that the following: that if you say that this is new physics, the structure is already quite constrained. There's only 4 operators that you have to worry about. Any others are either already constrained, so scalar currents would be killed by B sub S to mu plus mu minus, or they would come from higher dimensional operators, so it would be harder to build models. So there are only 4 which are relevant, and they are the O9 and O10. So we say that's the V minus A current on the quark side, and then the vector current for the leptons, or the axial current. And then there's also the primed, where I do the opposite. I have a V plus A current on the quark line. So the opposite from the standard model. Now, the nice thing with these transitions, RK and RK star, is that one is a pseudoscalar, the other one is a vector. So you probe different chiralities. So I have a spin 0, spin 1. So if you predict, let's say if we look at what RK would be, it would be 1 plus 2 times the vector on the current on the quark side, plus the V minus A on the leptons, and of course it's the difference between the muons and the electrons that enters because it's a ratio. This is all expanded to linear order. The RK star, in addition, also probes the right-handed current on the quark side. All right? So in terms of plots, would look like this. So RK star versus RK. And now, since it's a ratio, you don't know whether new physics is in muons or the electrons. It could be either one or the other, or the mix of the two, because the only thing you probe is the ratio so far. And then let's say you look at different options for the new physics. So this is the measurement, that's the standard model. So 1, 1. And for instance, let's say if you switch so this has V minus A quark current, but a vector on the leptons, it would be this line here. Or if you have V minus A, V minus A structure, it's this red line there. But for instance, you can't have right-handed times left-handed currents. So this already tells you quite a lot about the possible structure. New physics in the electrons, on the other hand, so all this is still true. I can have the vector current for the electrons, a V minus A structure for the quarks, but you can have right-handed currents for the electrons. All right, so it's easy to understand why. Because you need to suppress the ratios. So if I have right-handed currents that don't interfere with the standard model, so they will only increase rates. So I need to increase the rate in the electrons to be compatible with the experimental data. In the muons, it doesn't work. Now I would increase the rate in the muons, so this ratio would go up, which would be the opposite of what's measured. All right. So the upshot. These are clean observables theoretically, right? So these were ratios that are extremely well predicted in the standard model. It's the claimed total significance, taking everything at face value. That these are statistically dominated, the systematics are not the same, gives you more than 4 sigma. Now, what you can do is more. So why most people discuss new physics in the muons and not the electrons is because you can use more information, but this information carries a bigger theoretical uncertainties. Because you need to compare now the absolute values for the transitions. So you look at the branching ratios. For instance, this would be the prediction in the standard model. That's the data for a particular transition, B to K, mu plus mu minus. In here, there are form factors, so the matrix elements between hadronic states. And these form factors come from Lepton rules. Lepton rules have, it's an uncontrolled approximation. You don't really control, you don't know whether it's 20% uncertain, maybe it's 30%. So these bands are more or less guesswork. But if you take everything, so what you think is the right error bars, like reasonable estimates, they do tend to be away from the measurements consistently, in a consistent way. And now I have to also mention the P5 prime, which you maybe heard about. I won't even define it. So you can also look at the angular observables. The whole business started with this observable, which is called P5 prime. It's in P to K star mu plus mu minus. And just the name itself tells you a lot, no? It's P5, there's at least 4 of them, but actually it's at the order of 10 of the other observables. And the prime means that it was massaged to have a nice properties. So the claim was it's precise, but then if you look under the hood, there's a lot of uncertainties still there. So that's the busy thing here is these are the measurements are a bit above the predictions, but the predictions also, even though now people are doing really the same thing, more or less, there's still let's say a factor of 2 differences in the guesswork of how big the uncertainties are. So this, I would say, is tertiary. No? Tertiary is the right word, maybe. All right. So if it's in the muons, we can suspect that it's in the muons, but it requires more input, and you need to believe more about how well we control hadronic physics. All right, so the nice thing is that really taking everything at face value, it does fit together. Okay, so what's shown here is the best global fit you would get for the C9 and C10 operators in the new physics in the muons. So I don't know if you remember from the beginning, C9 and C10 were the ones that they introduced in the beginning. So V minus A current on the quark side. C9 is vector coupling to muons. C10 is the axial coupling to muons. And nothing else. So you switch on 2 operators, and then you do the following. So you take only the lepton flavor universality observables, so the ratios, so that's these blue bands, okay? And then you include the B to S mu plus mu minus global fits, and you will get this dashed line, or there's a different treatment of what the hell you do. For instance, everything is this red region here. Okay. So clean is blue, including dirty stuff is red, and it's basically right on top of each other. And everything seems to be pushing in the same direction. All right, so let's say we say that this is new physics, and we see what type of new physics this could be. So a reminder, right, the Wilson coefficients were in terms of the standard model normalization. So this would be in terms of so with this VTB VDS, this is 36 dV, and these coefficients that they had, they were order 1. No? Right, so the physics lives at about 30 dV if couplings are order 1. And then there's different ideas of what you can do. So 3-level or loop level. So 3-level. So either I have a Z prime that is being mediated here. So I have B left, S left, and then couples to the muons. You can either stick in a singlet or a triplet of SN2 or lepton works, either spin 0 or 1. So there would be a color flowing through this off-shell mediator. All right, so let's say you go for lepton works. So these are the quantum numbers. There's a finite number of them. There's one scalar one which fits. So in the last column, you have the predictions for what RK and RK star are. And there are only 3 that gives you RK and RK star below 1. So there are 3 leptoquarks that will give you the right pattern if you're mediated, if you're dominated by one mediator. All right, so then you can ask about the scale. And this is also, so they can be arbitrarily heavy, because you need to be in this band. So this is the mass of the leptoquark, and these are the 2 couplings to the BS and the leptons. So the new physics scale would roughly here would go as 1/m squared. When I have a contribution to delta MBS, this would go as a higher power of this couplings. So that's the upper bound on this, the value of couplings. So you want to be, so all this is excluded and the lower couplings are allowed. So this would give you an upper bound of what the leptoquark mass is, and for the 3 different cases, it's 40, 45, or 20 TeV. Right? So if you build a 100 TeV collider, it's not guaranteed that you will see the 45 TeV object. No. If you build a 500 TeV collider, you will see it. But if you start looking also, I mean, this was couplings which are any value. And so if you put in some flavor structures, what Gudrun and Ivan did was they put in some flavor models, and it will be like a typical range for, you explain the quark masses, there will be some suppression for B sub S transition. So you would really expect to be in the 1 to 2 TeV regime just from the flavor structure. But this is all guesswork, no? So we don't really know. All right. Now there's more. So, so B sub S mixing the coupling to B sub S to the Z prime. Oh, sorry, I switched to the Z prime. No? So for the Z prime, that's the main problem is really there are sort of two main constraints. Is the B sub S mixing, which constrain you to be like the small coupling to BS, even if you're at if you're at 3 TeV, for instance. So this is smaller than the standard model expression, about a factor of 4 smaller. And then you also have, because if these are V minus A currents on the muon side, then you couple to the neutrinos also. So there are constraints from this trident diagram. So you have a neutrino hitting a nucleus through a Z prime, which couples to muons. So you have 3 visible guys in the detector, so 2 muons and a recoil against the nucleus. So what's plotted here is the coupling for, let's say, L mu minus L tau model. And the non-excluded region is this shaded one, so B sub S mixing excludes this. And then the trident is this dashed line. So you're left in this region where you are at the TeV or so, with a relatively large one. So your marginal, where is the
So the white band is allowed, right? Then why that upper corner, it can, that circle can come down, right? Slide down.
Yeah, you still need to explain the anomaly. No, I don't see the
Yeah.
line here.
Yeah.
There should be a line for RK star.
Somewhere, okay, so that's
Somewhere, okay. No, I got
Okay.
confused about it. Yeah, but you want to be in this regime to explain the RK star. You need, okay, it's very, the way it goes, no? I have small coupling for B sub S, I have to have a big coupling on the muons. If I don't see where they go, sorry.
Yes.
Despite my blog. Okay. So one thing is these Z prime models, you like generically you'll have a problem because you couple to the left-handed guys. It will be very hard to forbid the diagonal flavor diagonal condition. So let's say if you look just at what's called the minimal flavor variation ansatz. So let's say I have coupling to the left-handed quarks and the leptons. So the couplings to the quarks will be, let's say I have from the symmetry I have an allowed identity, no couples to all of the quarks, all 3 generations. And then I just stick in the up and down Yukawas. Right? So it's an ansatz, let's see what happens. So if you do that, then immediately you have a problem because you will now have a transition which is proton-proton to a Z prime that goes to a muon pair. And this proton-proton will mostly pick up the first generation. So this first guy here is very dangerous. These other 2 guys are suppressed by the Yukawas, which are small for the first generation. All right, so just from this ansatz, if I have a diagonal which is allowed, so diagonal and universal, you will see that you run into problems because the preferred region for RK star will be excluded by the atlas searches, for instance, for the Z prime between 2 muons. Right? It's not super excluded, so if you have some other channel open, some extra vector like fermions, which are typically there in the UV models, you can get rid of these bounds. But you see that is not, so out of the box it doesn't work. So like all these guys work. All right, so that's what I wanted to say about the tree level. There's many references. What I'll do now is talk about the loop level. That's quite interesting, no? The standard model is at loop level, so, and even the new physics can be at loop level and you can still survive the constraints. So there are three distinct options here. We have either you put the loop on the quark side, on the muon side, or you just have like two mediators and two new physics particles that can run in the loop. So we'll see in the box. Okay, I'll pick that one for obvious reasons. No? That's the obvious reason there. And this is something which, okay, we were late to this game. Nobody thought about this because it sounds crazy, no? It really sounds crazy because I say I will modify the most dangerous thing, which is I will put stuff in which is colored. It will have to be relatively light. And naively we think this has to be excluded because you produce this tremendously at the LHC. But there's there's one thing that saves you, and it also explains a lot about the structure. This is true, of course. It's new physics. So first of all, it explains the V minus A structure. So we'll have something which will be top filling. The beta S transition will be due to the standard model W in the loop. Right? So we'll have a V minus A structure. We'll mix into this extra vector-like top quarks. Since it's top filling, it will get rid of this one here. So we will not have a problem with the Z prime production from the PV collision directly. So all this cross section will be lower. And you see that the constraints are avoided, even though the masses will be very low. And you could also search this in other signals, for instance, Decay to pi plus millipar. As you could see it, so LA62 is running right now. And in a few years they'll have 10% of the standard model. You have to look at the number in front. 10 to the minus 11 is the power. So this thing will be the standard model plus a correction here.
So if you change the Grom fusion, top group, then you can produce D prime.
I'll go over the constraints. Yes, absolutely. So, but that's, I mean, it's a loop factor squared. Yeah, so that's what saves it. 2 factor squared is 10 to the minus 4. Yeah.
No, but also it couples to B, so you can produce from.
Okay, so let's see. Okay. So because it doesn't couple to B, because it couples to the right-handed top.
So you did it for the right-handed.
Yeah. So
No,
of course.
So but the W.
Yeah, the W you get because you have a mass flip in the.
Oh, so
diagram.
then you flip the mass. Okay.
So what we do, I mean, it's very simple, no? Okay, it's probably not real, no? But it's like a proof of principle. It's a very simple thing. You just put the right-handed guy, couples to the right-handed tops, for instance. So let's say put a new U1, no? It's the minimal thing. The Z prime is the gauge boson U1 prime. I need a scalar that will break the U1. And then I need a new vector like fermion, and that's it. So then you have, so I take the coupling such that I couple to the right-handed top. So there will be a flavor structure here. This flavor structure will be taken that it mostly couples to the top, couples to the right-handed guys through this phi, right? And then, of course, I could write down the kinetic mixing, so we'll ignore this. We'll say that it's super small. You could also couple to the Higgs. We'll also ignore this stuff. So I just look at this reduced from coupling from this extra Utah. And the and what you would find is the following. No? So I have you mix. The mixing angle is big for the right-handed top. It's small for the direct mixing to the left-handed guy. But still, this loop is through the W because once I go into the top, I can put in a master. So you see so now you have so you really have the C9 and C10 are basically given by these couplings, and you see that you need roughly 500 GeV. Okay, maybe better than this is just showing the values. So for instance, what are the direct searches would be I single produce Z prime with the gluon, or I have a TT bar production with the Z prime. So all this is, you see, so this guy is 1 over 16 pi squared because I have two guys in the final state. So everything is about 4 orders of magnitude suppressed compared to the usual Z prime cross section.
So you have done a top seesaw type of stuff. So,
Right.
I see that.
Yeah. All right, so now, okay, maybe it's too much information. So you fix this to some, let's call it reasonable numbers. You need large mixings, but the scale is very low. No? So Z prime is at 600 GeV. This is the B to S mu plus V minus. And then the exclusions for the decays to muons. So if you had 100% going into muons, then it would be excluded. But of course, you couple to tops also. So and now depends on how you couple to exactly. It would be either 50% or 25% would be the lines. All right. So, and that's the trident search also excludes the people in the region.
So does this top seesaw affect this eco coupling, top eco coupling? Like this top seesaw you are doing, does this kind of affect the top eco?
Oh, the Higgs to TT bar?
Yeah.
No, I don't think so.
Okay. No, just I was wondering,
Right.
since you were doing this.
Yeah, because you would need to have both left and right guys to be big, but
you were doing just the right
Yeah.
part, the seesaw. Okay.
How radiatively stable is the alignment that you posit?
The alignment you positive, yes.
How radiatively stable is that? Under run?
Yeah.
No, I mean, like, I can think of, like, all this you just embed in the program itself. That's maybe the easiest thing to see. That's really fine. I mean, just the zeros are not zeros anymore. They will be down by a lambda to the,
Right.
to the 5, I guess. Essentially, it's all the couplings are the standard model in Dallas. So this would be big separations.
And this vector like T is mass of this vector like T, you say is 10 times.
Yeah,
Z
so
prime.
here we put them at, let's say, 5 TP, so I don't have to think about them.
Does it work without these?
Huh?
Does it work without these fermions?
Does it work without the fermions?
Yeah.
I don't think so, no, because then I have to gauge the top, and that's the end of the story, I think. Because then you put the top in the loop, and
You can't really give the top quark a mass, but it's just a standard bubble Higgs.
yeah. Okay. I don't think so. We can think more. I can think that. No, I don't think so. 10 minutes, no? B to C W.
No, we don't have that much of a constraint.
Huh?
We don't have that much of an upper limit. You can
Oh, yeah, you have to start
Such.
asking me questions and then I can
So
So let's see,
before you go, just one question.
Yeah.
So in the beginning, first few slides, you showed that you can change the electron, and then you mentioned something, the right-handed current. So if I modify by the right-handed current, then is it okay for the?
Yeah. Okay. So that's like there's very few papers that are written on this. No?
Yeah, exactly.
Yeah,
So
yeah. So what you need to exactly. So. So the reason why it was not written is because you have to say that the Lepton sum rules are off. Okay, they're systematically off.
Yeah.
Exactly. That's all. I think that's the only real assumption that you have to throw away. Once you do that, I only have ratios. Okay. And then you can do whatever you want. Now it could be muons, electrons, it could be electrons, and it could also be right-handed electron currents.
Okay. So then, Lepton sum rule, I don't have much of a faith in that. So, but now the question is, suppose if I forget that, then also this C9 to C10 correlation is what we do based on non-universality. And at that time, if I throw out, then also it would affect my understanding of the amount of flavor values. I can also attack it from that viewpoint. Like, see,
okay, I don't quite understand, but we can go back. Oh, it doesn't show the numbers in there. So I have this plot.
yeah, the famous guy now.
Yeah, sorry. Yeah. So this thing here, no? And I had numbers here. So this has to be quite big. I think it's 4. So 4 times bigger than the left-handed guy. So you would have to, okay, it would be, in terms of the scale is twice as low. I don't know, I mean, instead of 30, it's 15.
Yeah.
Who cares? No? Still, but I mean, you could write much more interesting models.
Yeah, exactly, because you work on the right. Actually, I'm also stuck with one such case. And
oh, you wrote a paper?
No, I'm stuck with one such case where I have the B2 RD star, but RK star, I need to do something.
RD star. Okay, let me talk about RD star because there is also the right-handed currents are interesting.
Yeah.
And you could, in principle, marry the two through right-handed currents.
C9 minus C10 is
but
not
it
one.
will not be exact. Okay, let me go over this and we can talk maybe about the future projects. So the upshot here is the transition is charge current. So again, theoretically clean, 4 sigma-ish. But the difference is that it's large. This new physics effect is large because it's 20% of standard model, which is a 3-level now. It's not an FCC, but charge current. So I take this W exchange, the only separation on top is VCB, and that makes it much harder because many interpretations are in conflict with other constraints. All right, so I'll do a lightning review of the experimental situation. There are 2 observables here. It's either B to D or D star, so this meson or vector meson. So that's what's plotted here, the 2 observables, and then there are many more measurements. The standard model is this small region there, and the experimental global world average is this red region here. Or if I blow it up, so this is from Dean and company, so you can try to play with the standard model predictions. It's very robust. You have to, I mean, I don't know, you have to be completely crazy because everything is controlled by HQET. So even if you compare, if you forget about lattice, the only thing you're putting in are HQET up to 2nd order. It doesn't get much bigger. So we're far away from the experiment. And the reason is very simple also. There's only one form factor which is not common to the 2, so many things cancel. All right, so if it's new physics, again, it's an experimental issue. And so without some rules, you see it's still very far away. All right. Okay, so then, so there are let's say that you assume, so what you see in the experiment is B to C, tau, somehow tagged, and then a missing energy. So let's say that this tau is also the same as in the standard model. And then there are two options, right? Once you do this. There's either you have a charged current, which is a color singlet, or you have a charged current, which is a color, carries a color. Should be out there. Alright, so this would be lepton quarks. These are the W prime and the Higgs. And then it's a long table from Zupan, but it's a finite number of these guys. There's two color singlet mediators. You should look at this middle column. So there's 6 lepton quarks and 2. So it's a finite number, but not all of them fit. So for instance, if you take a color singlet, you have a W prime or a scalar doublet. Color triplets are lepton quarks, and the typical mass is about 500 GeV. So that would be these guys here. Got 4 options here, and many of them are ruled out. For instance, like, the first thing you would think is a charged Higgs, no? That doesn't fit. Doesn't fit from many sides. If you look at the total B sub C lifetime, it excludes the charged Higgs there. If you look at the Q-square distribution that are measured in the actual experiments, let's see the anomaly, doesn't fit. And then with some, let's say, small flavor assumptions, you're also excluded from the tau-tau insertions at the RNC. Then the W prime, again, here you have a problem that this is part of a triplet, so you have a Z prime, and then you're dead because you will produce too many taus at the RNC. So you're left with the lepton quarks, and some of them are also ruled out. The problem here is the following, that all these guys here are coupled to the left-handed guys. So let's say if you look at the lepton quarks, you have this left-handed quarks, and then roughly what you can do is you can minimize the coupling to the right, to the first generation. For instance, you would say, okay, I have only B left, and then I have these small couplings to U left and C left. So B to C TAMU is VCB suppressed, but still you are dead from the researchers. Okay, this is for the scalar. Let's keep this. Z prime, no? So Z prime. So what's plotted here is a bit convoluted. So that's the Z prime mass, and they keep completely general how wide this can be. So you can have other open channels. So this is quite conservative, and then you fix the couplings that you need for the B and the lepton, so the quark and the lepton, to some value. That's this product here in dimensions of V over mc squared, and this is what you need for the anomaly. And the anomaly numbers were here, so I need 2.9 for this roughly. So this number, which is 0.3, should be so this is allowed, this is excluded, and I always get confused about this process. Damn under. Let me see. Yeah, I think that the story is, yeah, this is the number I need for the anomaly. This region here is excluded. This is still allowed. This is allowed. So it means that they have to be at very small masses and big values of the decay width. So here it's even worse if you go to higher masses, then you have to be in this regime. And there are two different searches. No? So at 0.6, they are incompatible. No? So you have to be.
So, but
I'm not sure actually. I don't know.
yeah, and also Atlas does not go to 50% for any.
No, they don't. So that's their interpretation. They
Okay.
recast the. Yeah, no. So they do a smaller decay width, but they recasted the searches.
And tau especially, it's less than 10%.
The tau?
Yeah, because for jets I've seen something they are going up to 30%.
Yeah.
But everything else I've never seen beyond 10%.
Yeah, well, okay, secretly they would always tell you that they did it, but they never published this. That's true. All right, so anyway, so you see what you need, no? Is you need very wide decay widths, so you're in the non-perturbed. I mean, if you're at 30%, it's really doubtful that you know what you're doing theoretically.
So what Atlas assume for protection?
What was that?
What they assume for the protection of the from the QQ?
So yeah, so you do, okay, so you do BB bar.
So they assume VB bar.
Because that's VCB enhanced. So it was a bit quick. All right. So there is a particular structure here. Okay. And you see that if I want to go from B to C, I will pay a VCB. But then for the Z prime, I pick up BB.
Right.
So that's the main production is BB, but it's because you tuned it to B. No?
Yeah, that's part
So
of I know. So
Okay.
for Atlas, do they assume?
The Atlas doesn't assume this in the search, no?
So how do you interpret?
So what they did was they just took Atlas search
Yes.
and they recast it with the
Okay, I see.
BB initial state,
Okay.
and they tried to mock up the large decay with
Okay.
looking at the data and trying to do their own bomb hunting.
Okay. Thank you.
Okay, I think I'll skip this. So it's the same story. What I wanted to go is to the right-handed currents, because a lot of this had to do with the fact that you would have a left-handed quark would have now mix. I mean, it would be hard to engineer a flavor structure such that I would kill most of the stuff that gives me constraints. But with the right-handed quarks, at least in principle, you can do this. All right. So the difference here is that I have a standard model process, but then instead of having a left-handed quark here, I have a new guy here. Right. So a stellar guy, if you want. So these two will not interfere, will be just a coherent sum. There's a price to pay, so they have now a square of this diagram. But the nice thing is that, of course, it predicts just an enhancement in the two ratios, because it just add extra transitions. They look the same for the experiment, of course. All right, and then, okay, so now you can go to the list of possible mediators. There's only 5 of them. There are 2 color singlets, 3 Lepton quarks, and then so they all are consistent within 1 sigma. So these are the 3. Some of them are just lines, or you have more parameters to cover a plane. But they all lie above where the data are, because you enhance the rates. All right. Now 2 are dead because you just look at 2 different observables here. They will just kill them. So we're left with 3. And then there's also this issue of how big the neutrino masses are. So at 2 loops you would generate from this operator. You would generate a contribution to the neutrino mass. And then for the Lepton quarks, if you just have all the couplings allowed, you would regenerate neutrino masses that are, let's say, 2 orders of magnitude above the standard model ones. That's the to the contribution to the standard model neutrino masses. So that tells you that actually from the low energy point of view, you will predominantly just generate this operator. So right-handed port current and a right-handed electronic current. And this you can do. All right. So now, so I won't do all the Lepton quarks. I think the W prime is more interesting. So W prime will give you this structure, no? The right-handed and right-handed. And it's a super simple model, no? Because what you do is just you extend the gauge group by another SE2V, and then you break it. The breaking is not so important. You can do the most naive thing, the same as in the standard model. You put the doublet and you break it down. And what you need is now an extra set of vector-like fermions. So you can have 1 or 2 or 3 generations of these guys. You can charge under the SE2V, but otherwise look like the right-handed quarks. Right? So there will be large mixing of these guys with the B right, C right, the right-handed neutrino, and the new right. And the reason why this is that the vector-like mass term will be smaller than the coupling times the VEV of this HV. Right? So if you couple to the vector-like quarks, the mixing will be more than 45 degrees, it will be closer to 90 degrees. They're mostly the vector, like the standard model B right that you see is mostly coming from the component of the vector-like quark. All right? This makes sense. And then, let's say for the right-handed neutrino, it's a similar story. Okay, would be so just as if you look at the single generation. So I have now 4 guys. So this would be the neutral components of the vector-like leptons. Then I have the standard model right-handed neutrino, the standard model singlet, and then I have the standard model left-handed neutrino. So 4x4 matrix. And then, okay, so you can write the Majorana mass term for the new right. So let's do some simplification. For instance, if I take the vector weak equals to 0, or this y new equals to 0, then you can just forget about this new left components. So if I look at this 3x3, for instance, if I have mu equals 0, then I have a massless Majorana neutrino, and then a set of an Dirac fermion. And this massless Majorana is just a mixing between this new right C and the N right. And here again, it do the same thing. So the lambda V times V nu, VV, divided by the lepton vector-like mass. This needs to be big, so that the mixing angle is big, and then this massless Majorana is mostly coming from the guy that carries the SE2V gauge. No? All right, so now you see you have a big coupling to W prime. Okay, then you perturb this. Mu is non-zero and so on. Right. Okay. All right, so now, I mean, the real benefit is now that everything is in the right-handed sector. So you can engineer the flavor structure, which is completely minimal. No? So you just couple to B, C, and tau. And there's a radiatively stable model that you can write on where that's the only thing that you generate. So what are the energy constraints? Well, of course, now you produce the W prime, it decays either to tau and right, or it could decay into the vector-like states also. Or the Z prime the same, no? And this would be in the ratio of 1 to 3, for CB and tau. Times whatever this goes into the vector-like fermions. For instance, if I have one family, so that's the minimal thing that I need for this to work. Right? So the minimal field content, the RD star band is here. That's the VEV of this HV. The coupling that is allowed is very close to non-perturbative, though. These are the excluded regions. If you have two, it's a bit better, so it's a coupling of two is kind of allowed. Now, because this was the simplest thing, right? You could modify stuff. For instance, instead of the doublet, you could go to a triplet, break it by a triplet. Then this thing will move further up. The VV that you need effectively would be, or the bounds would be lower in terms of VV, because you get the in order one couplings enter when you compute the W and Z masses. Okay, so this I think I will skip. So there's one set of models that people discuss where you can explain both. It's a Lepton quark vector model. So you essentially write on a Patti-Salam type models, but modified. So there are different Patti-Salams for different generations in order to avoid flavor constraints from chaos. So that's all right. The future is bright. We will either kill this or discover, because there is LHCb has an upgrade that was approved up to 50 inverse femtomers, but then they're thinking about 300. So that will be roughly, I have these estimates. For instance, Bear2 just started, okay, they don't have the inner vertex detector yet. It's coming, they shipped it to Japan just now. I don't know if you've seen this photo. So the way they ship the vertex detector is on the Lufthansa flight on the bed of the pilot, so that it doesn't get disrupted. So they will install it quickly, and then next year will be the real B-physics data taking. It will be roughly 50 times more statistics. So in terms of the new physics reach, take the fourth root. That's about 2.7 times whatever we have now. Right, so okay, for the LHC aficionados, it's going from 13 to 35 dB. So it's a big gain. And similarly for LHCb, so they could even end up with 100 times more statistics than they have now, because they are also going to a full software trigger, and the cross sections went up. All right, so sorry for going over time. So what did I talk about? B2C TAMU, B2S mu anomaly. It's very intriguing. I don't know if it's real or not. My bet was that this B2C TAMU would go away. It was first appeared 5 years ago. The scale is so low I couldn't believe it. So for 5 years I didn't write a paper on this, and now I gave in. Then there's the B2S mu anomalies. There, of course, the worry is it's only one experiment. So, okay, would like to see this from there too. There is, I didn't talk about this. CMS has now data parking, so they will also measure something, okay, something useful. Hopefully they can measure duration. It's not a bug, it's a feature, no? So interesting model building challenges. So you can hopefully, if this is real, no? It's not completely hopeless. There are models out there. They don't look very convincing right now yet. And the really important thing is it will be tested. No? This is something that is in principle testable either from low energy or direct production. All right, thank you.
Thank you. Are there any questions?
Question. Going back to heavy neutrino case, that's W prime decay. And how we can predict from usually the right core fusion?
You mean the W prime production?
Yeah.
Yeah. So this came from BC. BC. That's the minimal thing that you need. Huh? Just You only switch B right, C right coupling, and that's it.
And if you have G prime, can decay to be neutrino?
No, Z prime cannot be B and
G.
So Z prime, okay, so Z prime,
either
Yes.
B or
so as Z prime goes to tau tau,
Yeah.
the neutrinos, the right-handed neutrino guys. So the new R that I call
Yeah,
it.
yeah, yes.
Sorry, the NR, the same B to C tau NR.
See, my question was, G prime can decay to NR, right?
Yes.
That's my question.
Yeah.
so to repair them, basically.
So like the minimal thing that you have now is you couple to the B right, C right, tau right, and NR. You can decay to all these 4 states.
And do
And
you have
then-
any preference of mass relation between WR and NR?
Oh, sorry.
In mass relation between the NR and the WR?
NR and W. So there is as
What
in
about
if there is any mass relation. So WR mass could be any TV, so whether NR has any.
Oh, whether they have to be there? Yes, because there was this, yes, absolutely, that's a very observable point. Yes. It was a coupling, whatever these Yukawa couplings, VV over the mass. No? So this could be either the vector-like leptons
Yeah.
or the quarks and the Yukawa. So these Yukawas, of course, I can't push to be more than, let's say, 3. So now the mass of the Z prime, when I take the VV, of course, there's a G of the group that also enters. But again, this thing now, okay, so if it's small, then I have a problem with the B2C TAMU, so let's keep it to be 1. These guys need to be light. Let's say 1.5 dB-ish. Right. But in reality, you want to keep them even lighter because the W and the Z prime need to decay to the vector-like fermions in order to avoid constraints. If they're too heavy, then you see these bounds become even more severe. Okay, I don't have a plot. Yeah, this already assumes that you decay to one vector-like fermion family. So here we took them to be at 900 GeV. It doesn't matter now, but 900 GeV is the present bound for this for the vector-like fermions. This type. But okay, there's a room now. There's maybe push it up to 1.3 dB-ish. I don't know.
But
It's still fine, but you cannot
the
be much
equation
heavier
is
than
or NR.
After looking for the mass relation between the front and NR, like half of the mass or.
Right, so right now, so exactly, yeah, so there is this one, no? Just from the mixing I have a constraint, but phrenologically I have yet another one, which is that I want them to decay into the vector-like fermions, because then it reduces the branching ratios into the, let's say, tau plus missing. Yeah, and these vector-like fermions, the bounds are at about 800 GeV right now. And you can, let me see where you are. Well, that's
The box
really,
B2
so it's not
stuff.
directly converted, it's not the mass directly, no? It's roughly, so, 1.3 dB, I don't know, maybe 1.5 dB. But you can't arbitrarily just decouple this stuff, no? Because it's anchored to the B2C downhill. You can't just.
Yeah, actually, we are going to about paper.
Okay.
That we want to NR, same kind of state, but we are assuming for very fine for this source, the right cox.
Okay.
So if we can scale down somehow, so BS, maybe we can reset the limit on the GPs.
Right. Yeah, this would be nice, yeah.
Yeah, it's within result.
That's CMS?
Yeah.
Yeah.
Probably its rate will change because it's about submission.
Or maybe the internal referee will be on.
Yeah, friendly kind.
Okay, you can take any other questions offline. Thanks, big one. We can get coffee.
Very nice.
This is a strategic error.
Yeah.